Hey guys, this is Tallen bringing you another tutorial today on something we're doing in engineering classes. Today we're going to be taking a look at PLC, that is programmable logic controllers. I'm going to be walking you through how to design a basic system like this one. We're going to take a look at how to design it on the physical side, and I'm going to run you through how to do it on the digital side. I was not able to install the Rockwell program that we use to run the simulations for these, so I'm just going to be drawing up the circuits and the logic diagrams, and if you guys want to test them, you can go ahead and test them yourself. These are not going to be the best methods, I'm sure, the industrial level, like professional way to solve these problems. However, they should help you if you're kind of new to this subject or if you're struggling to keep up. So let's just go ahead and take a look at this. So here we are designing a system in order to mix a liquid and heat it up before pumping it out. We can see we have the design specifications up here. We have a start and a stop. The start is normally open and the stop is normally closed. So basically what this means is that we'll go into a little bit more detail later about what normally open and normally closed mean. For now, let's just talk about the rest of this. Only normally closed type is available for the limit switches. The event sequence is fill the tank, heat and stir the liquid to the temperature point and hold for 30 minutes, empty the tank, and repeat from steps 1. We can see down here we have some clarifications: heat and stir the liquid to the temperature set point, stop stirring, start timing, keep the temperature at the set point for 30 minutes. After 30 minutes, stop heating, and then of course it's going to pump it out. We also have a nice diagram here of all of the different labels that we're going to be using. We don't have what the outputs and the inputs are going to be for the physical system, so I will just use these generic tags and refer to them as such. So let's go ahead and talk a little bit about PLCs. So PLCs, they're a little bit different to how you would typically write a programming language. For instance, in what is called structured text, that is, oh my god, my handwriting is so bad. Structured text is kind of what you are familiar with when you think of programming. Whereas PLCs are going to be working a little bit differently, so I'm just going to talk about some of the differences. The primary thing that we're going to be working with basically is if statements. So if you guys have ever used a structured text language, basically what we have is if X, then Y. That is kind of the common baseline for everything that we're going to be working with. And it's basically the same for PLCs, except PLCs we're going to be using different symbols. So the primary symbols that we're going to be using are going to be these contacts. They're going to look like this. This is normally open, otherwise known as NO. We also have normally closed, NC. And these actually translate really well to each other, the if statement and these normally closed. So for instance, if we have if X then Y, if we wanted to write that out in PLC logic, we would have if X then Y. And that is what that would look like. And what the machine is going to do is it is going to go ahead and run the code, basically, that we have, and it's going to run it from left to right, top to bottom, and it's going to say if X is true, then make Y true, for as long as X is true. If we wanted it to be something a little bit more along the lines of if not X, then Y, all we have to do is we have to change this normally open contact. We would change that to a normally closed contact. So, but normally closed is true by default. So basically you have to imagine it like a, let's imagine it like a drawbridge. So if we have like our little like bridge here, let me see, I have a minor in art. Yep, there's our little drawbridge. So when it's like this, no cars are able to get to the other side of the road. If you're like a little car who's over here and you're trying to get over here, you're not going to be able to cross this bridge because it's open. However, once the drawbridge closes, now all of a sudden you can go ahead and cross this bridge. So you have to see that in the same way that we see our ladder logic. So it's actually roughly the same shape. So when it is closed, when it is closed, it's going to be crossed. When it's open, it's going to be open. And again, you just have to imagine that cars are not able to pass. The signal is not able to pass across this line before that gate gets closed. So let's go ahead and start analyzing our problem. The first thing we have to do, however, is we have to make a physical representation of what our circuit is going to look like. So I'm going to go ahead and name this physical, and this is basically going to be our circuit. Most of our effort is going to be spent building this physical circuit, and then after we're done with the physical circuit, we'll spend a bit of time making the digital circuit. So if I pull up this sheet right here, whoops, we can see here are the symbols we are going to be using primarily for our physical logic. So I'll be referencing this a few times as we go on, but we can see the important ones that we have are push buttons, limit switches, temperature switches, and our control switches and our timer delays down here. So I will reference those when I need to. But for now, let's start talking about what our circuit needs to look like. So the first thing that we need is we need a start and a stop switch, and our start is normally open and our stop is normally closed. So that's very important. Most of the time when we design a stop switch, we are going to be using that same setup where start is normally open and stop is normally closed. I'll go into detail about why that's a little bit important going on, but for now we have to design a way. This is a super basic concept. It is a way to make a self-locking variable. So how do we get a variable to self-lock? So when we're designing PLCs, our variables are going to go over to the right side, and we will call this power. And all of our inputs, our if statement, is going to go kind of in this side. So how do we get something that's self-locking? Once we turn it on, it never turns off. So what we are going to do is we are going to do... So this is our normally open physical switch. This is our, not power, this is our start. Per chow. So if we do something like this, we can see that the way that this is laid out, once you hit this physical start switch over here, I wish you could see my mouse. I think you can if I do this. Nope. Once you hit this physical start switch over here, power will be on as long as you keep that switch flipped. But the moment you take away that switch, power goes off. So we don't want that. So how do we keep power on? Well, what if we just have an OR statement by bypassing this for power? So by putting these in parallel here, we can parallel series? Parallel, yeah. By putting these in parallel, what we've effectively done is we've made an OR gate. So by this, we say if start or power, then power is going to be on. And since power references itself, you'll notice that the moment we hit this start switch, we're going to get power, and that power is going to stay on even if we turn off our power. However, we do need a way to stop this once we're done, so this is where we are going to implement our stop switch. Chow, just like this. And it's going to look like that. So now the way that this works is our signal is going to flow through once we've hit our start. And as long as the stop switch isn't hit, it's going to continue flowing into power. However, the moment we hit our stop switch, this circuit is going to become disengaged, and all of a sudden power is going to stop flowing there, and all of a sudden power is going to turn off, which means that everything preceding this little circuit will stop. I know this is kind of going a little bit more in depth on this part than you may want. However, this is kind of the core for everything we're going to do past this. So I'm really trying to drill down a lot of these ideas in your head. For now, just know when you're working on stuff in your own, if you design anything in series, like this, where they're kind of going off of each other, this is effectively AND. So if we have X and Y. However, if you design anything in parallel, it's going to be an OR. So this would be X or Y. Okay? I guess I can leave that up. Okay, so now we have our circuit is powered. Also note that if we take a look back at our original document, This one, the start switch is normally open and the stop switch is normally closed. We have incorporated that here. We can see that the start is normally open and we can see that our stop is normally closed. We will adjust this as well once we get to our physical sketch, but for now, just know that we've kept that part intact. So, what is the next step that we go from here? Well, we want to start filling our tank because it's empty at this point. So, we can just do V in. But now we have to ask ourselves, when do we not want our tank to start filling? Well, for sure, we don't want our tank to fill when there's no power. So we're going to have a normally open gate there for power. The other time we don't want our tank filling is if our tank is full. Because obviously if we filled when our tank was full, that would cause some... The other time that we don't want to fill our tank is when our tank is full. If we kept filling when our tank was full, that would just lead to spilling, and that would be a mess. This symbol that I've just drawn here is the closed symbol for the limit switch, as you can see right here. Also note that I've used the normally closed variant of this as well, because as specified in our design doc, that all of these switches have to be normally closed. So the last thing that we don't want our tank to go off with, and I'll explain why later, is if we are currently emptying our tank. So these are kind of the three things that are going to keep our tank filling. So we need power from this. We need to make sure that our tank is not already full, and we want to make sure we're not outputting anything. So as long as those three statements are true, it is going to start filling up our tank over here. Moving on, so once our tank is full, where do we go from there? Well, we need to start heating it and we need to start stirring it. So, like always, I'm going to go ahead and start with the power, because we basically always want power. The next thing I'm going to do is, let's think about this. So I'm going to put heat over here, which is just denoted by an H. So, when do we want our tank to start heating? Well, we want it to start heating when it's full. So what we can do is we can put our full indicator right there, full limit switch. However, note that this is normally closed, which means this is active when our tank actually isn't full. It's inverted. So there's nothing really we can do for that right now. However, I'm going to circle this just to remind us that once we move on to our digital sketch, we are going to want to invert this digitally. So going on from there, when else do we not want our temperature to be heating? Well, we don't want our temperature to be heating when it's at temperature. So I will go ahead and I will sketch in a little temperature, and this is going to be temp. This is just a little temperature controller. As you can see, I've made it normally closed as well, just so as long as it is not temperature. Again, anytime they are normally closed, when these two are bridged, it is effectively inverted. So it's another way of saying when our circuit is not at temperature. If we wanted it to be at temperature, what you would do is you would just go ahead and change this up, and you would make it normally open. So see how they're not connected now? There's no circuit flowing through. That would be when it's at temperature, but as previously said, we want it to be when it's not at temperature. So we'll do it like that. The other thing that we have to keep in mind is when it is going to stop heating, finally. So for now, I will just say, we'll do, we need something here, okay? Something to tell it when it's done. So for now, I'll just put done, and we'll come back to that in the future, and I will circle this just to remind myself that we need to do something else there. So now our tank is going to be constantly heating up. Every time it comes to temperature, it's going to stop heating, but the moment that it lowers in temperature at all, this thing is going to fall, or this thing is going to go back up, and it's basically just going to keep like bounding up and down repeatedly and keeping our tank at temperature. So now that we've sorted that, we have to think to ourselves, when do we want this to be stirred? So, stir. Obviously, we want it to stir when the power is on. Let's see. Just like the heat, we want it to be stirring when our tank is not tank is full. Because again, don't forget these are inverted when they're normally closed, so this is actually saying when our tank is not full, but we want to re-invert it, so I'm just highlighting this for now, so that way we can design it into the digital stage. Hopefully this will make hopefully this will make a bit more sense once we move into that phase, but for now, just try to hang with me. The other thing we are going to need is we don't want it to go. Once our kind of done trigger up here triggers, we also want this to stop, but we don't know how that's going to work just yet, so I'll just go ahead and highlight this. And there's something else we need. So the difference between the heat and the temperature, if we take a look at our design document, we can see that once it comes to heat, it heats up and stirs until it gets to a set point, and then it stops stirring and starts a timer. So once it hits that temperature initially, the stirring needs to stop, the heating needs to continue, and we need to start a timer. So how are we going to do that? Well, we can think about that a little bit more, but we do know that we are going to want to stop it once that timer's up. So TR1 is just our reference for our timer. Once again, it is normally closed, which means that once the timer activates, it is going to open up and it is going to stop all the signal going through here. So now let's think what we need in our other locations. Well, I think this done actually should be a timer as well. Oops, I just erased something important. Boop, boop, boop. And I think that solves that. So let's take a look at this. So when we have power and our tank is full, as long as it is not to temperature and the timer has not gone off, it will heat. That makes sense to me. Everything seems good there. Let's take a look at down here for the stirring. If it has power and the tank is full and there's still a step we're missing here and the timer has not gone off stir. So what is this step? Well, we actually need to figure out once it's gotten to temperature once, and then we need a variable to control that. So what I'm going to do is I'm going to make a new Boolean variable that we're going to use down here. And I'm just going to call this @temp. And our @temp variable is actually going to be what controls this. So our stirring is going to happen as long as we are not @temp. Again, I've made this normally closed, which inverts it. So it is saying as long as we have not activated this @temp variable, it is going to continue stirring. But the moment we've activated this variable, it will stop stirring for the rest of our cycle. So when do we want this @temperature thing to go off? Well, we want it to go off the moment that our temperature hits for the first time. So once again, I will go ahead and add our power. And this is going to be another self-locking variable. We've done this in the past, so I'm just going to do it again. But this time, what's going to control it is a temperature. So there we can see once it hits temperature, it's going to turn on that @temp, but we want it to stay on. So I'm going to set it to be self-locking. Just like that. And finally, we need a way for this to eventually turn off. I think, just like everything else, it will turn off once our timer goes off. Because that timer is basically going to kind of be a big reset for a lot of this program. Oops. So let's take a look at this. If we have power, and once the temperature goes off and the timer has not gone off, @temp is going to activate, which is going to keep it active forever. Once @temp is activated, we can see that our stirring is going to stop. Well, what else is going to stop when the stirring stops? Well, our timer is actually going to start. So, oops, that is the wrong color. So, if we have power and @temp is activated, notice how this is normally normally open now because I want it to be when it is active and not inverted. Then we are going to start our timer. And our timer, again, is just going to be TR1. I'm just going to say that this needs to be 30 minutes. Once that is active, it will... Let's take a look. Once 30 minutes have gone by, it will turn off @temp, it will stop the stirring, which the stirring actually should already be off at this point, so I think I can remove this, actually. So I will remove this. There we go. And it will also stop us from heating. That all seems good. Now we're kind of finishing up here. The last thing that we need to do, now that our temperature... So our liquid has officially been heated up. It has been stirred. All that is left is we need to pump it out of the system. So for that, we are going to have a power. And once our timer has gone off... So because I want this to activate once our timer has gone off, I'm using normally open, or because you can see here, this will not activate until the timer has triggered, which pushes this up. And finally, I do not want it to be emptying once it is fully empty. So I will just go ahead and do LE. That is the symbol for once it is empty. And we will output it there. So taking a look at what this does, once we have power and the timer is activated, and it's not empty, because again, normally closed inverts it, it will start emptying. Vout, again, just to reference it, just in case, Vout is the pipe or the pressure, whatever it is using to remove the liquid out of our tank. So that is all working nicely. I would also recommend at this point taking a look back at what your system looks like, because it is very possible that you might have created a system that accidentally does something that you didn't expect it to in the future. So let's go ahead and take a look at our very beginning again. Once we activate our start switch and stop has not been activated, we are going to get power that is going to trigger the rest of it. If our tank is empty, if our tank is not full, which is this, if our tank is not full and output is not going, then we are going to feed into the system. See, if you had actually forgotten something like this V output, which of course I didn't forget because I already designed this circuit in the past and I'm just redesigning it and explaining my thought process. If we didn't put this V output right there, the moment that we had gotten down here and started this V output, our tank is no longer full, so it would have began putting more liquid in. So you would have been putting liquid in your tank and out of your tank at the same time and achieving a whole lot of nothing. So I would definitely recommend thinking about every possible state that your system is going to be in. Just because you're already working on like rung 3 or 4 down here does not mean that you can forget rung 1 up here, because maybe you're going to do something to this rung that will reset this rung and mess up your entire program. So this is looking good. The next thing that we are going to do is we need to turn this into a digital system. And turning from a physical system to a digital system is pretty easy. It is just going to be how we are going to be handling these inverted pieces. But everything else should be pretty simple from there. So I will go ahead. I'm actually going to select all of this and scale it down because I would like to reference it. There we go. So now we can go ahead and start working on our digital system. So the digital system is going to be the exact same thing, except we're only going to use those contacts and those inputs and outputs that we showed before. So this is, I guess I can make it a little bit bigger just in case. This is our digital system. So now we're basically going to redesign it using traditional contact probes. So we no longer use the push buttons and stuff. We are just going to translate this here. So if we want to invert something, if we want to keep something the same way, we are going to use a normally open. However, if we want to invert something, we are going to use normally closed. So up here, this start switch is looking good, so we can leave that as a normally open. We can also keep this power as the exact same as a normally open as well. And our start, we also want to keep this as normally open. And I know this now seems backwards, where we have normally closed over here and now normally open over here. But that's because we are translating the physical signal into the digital signal. So what this is saying over here is when the start button is pushed, this will be false, but until then, it's true. So, what do we want this to be? Well, we want it to be true until it's pushed, and then it'll be false. So actually, by using normally open, we are keeping the physical signal into the digital signal. And if you guys don't really understand what the difference between the physical and the digital is, this is how it is wired in the real world, but this is how we are going to program it in our PLC controller. So most of the time when you're using start and stop buttons, in the real world, they're going to be normally open and normally closed, respectively, but you're always going to want to use normally open inside your digital circuit. It's super important that basically every time you see stop, even though you want it to be normally closed, because that makes sense, you actually want to write it as normally open, because otherwise you're going to be inverting the signal and it's not going to work. And we can just keep the rest of this into power. Next up from there, we can keep most of this. We want to keep that the same way, so this is power. And this is L up. And that we are keeping as V out. And it really is this simple. So things you want to stay the same are going to be normally open. Things you want inverted are going to be normally closed. From there, we can move on to rung number 3 with power. And this is where it's important that I highlighted these, because we actually want these to be normally open, however they're normally closed in our circuit. So to invert them, we are going to use normally closed here. And now we could do L up. And temp. And timers. So timers work a little bit differently digitally as well. There are a whole bunch of different timers, but basically most of the time we're going to be using TON timers. What these do is they turn on after the elapsed amount of time that you input for them. To reference their output, we are going to use TON1.Q. That is their output, and that'll make a little bit more sense once I get to that part. H. Moving on from there, we have these stirring lines, so we have power. We are again going to invert L up, because we made sure to note it here that we wanted it inverted. We want at temp. So this is actually an internal Boolean, the way that we've used at temp over here. So this isn't any real physical input or output. So we're actually going to mirror those the exact same way in our digital circuit. Because even though this is a physical circuit over here, not all of these are physical switches. For instance, at temp is actually an internal computer Boolean. It is not a physical switch that anybody is hitting. So those are going to be translated one-to-one. Stir. Power. At temp. And this is where our timer is going to go. So timers, they actually load up as large blocks once you're doing them physically. And they have some important stuff. This is the input. I don't remember what it's called, so I'm going to call it in. The output is called Q. There is also, what is it? It is, I think, PT and ET. ET is the elapsed time that has gone by since it is received signal. PT is whatever time you're looking for. So to input the amount that you want your delay to be, and this is our TON1.Q, by the way, you are going to use T, hashtag, the amount of time you want, and then whatever unit of time that is. So in this case, I'm using M, that stands for minutes. You can also do seconds, milliseconds, hours, days, maybe months, depending on what PLC you're using. I'm not 100% sure, but for now, we are just going to use T hashtag 30 minutes, and that is going to set our timer. The last thing that we need to do for our digital circuit is the output. So power, TON1.Q. And you can see now that we are referencing the Q output right here in our system. we are basically asking like, hey, or actually, sorry, this is not Q, this is just TON1. So we were saying take TON1 and find its value of Q, which is whatever the output is. You can also technically build circuits on the other side of your Q. So for instance, you can put stuff kind of in this space, but for the most part, I would recommend just kind of using as many rungs as you need to and kind of just making your program as legible as you possibly can. The final thing we need here is our limit switch. I do not need to invert that, so that is LE. And finally, V out. And there we have our circuit. Again, I wish I could build it in the physical machine, but I just could not get that program working in time. So let's go ahead and take a look, and I will try to basically simulate what it's going to do, hopefully give you guys one last look of how it works, and maybe a little bit better of an understanding. So at the start, we are going to get signal here. Let me see if I can make that a little bit more visible. How's red? There we go. We're going to get signal here, and then once we hit start, this is going to close, and it is going to let signal go here. Our stop is normally closed, so signal can actually pass through here because that's already true. And it's going to activate power. Because power is activated, this line gets activated. And now even if we stop using start, whoops, our signal already has a way to circumvent start, and it's going to stay on as long as we don't hit that power switch, or the stop switch. Now, we have power, so this L up, oops. So again, this L up is going to be true over here just because this is normally closed. So as long as our tank isn't empty, and as long as our output isn't going, which it is currently not, our input is going to start triggering. Cool, it's looking good so far. Taking a look a little bit further, power is on. It is going to wait until L up is full. So once L up is full, this will close and all of this will deactivate. It will no longer feed liquid into our reservoir. Then it will pass signal through here. Temp, again, is inverted, so this is true. Our timer is inverted over here, so this is true as well, and it is going to start heating. And as I mentioned before, the temperature is going to keep springing around as it kind of hits temperature and goes above. So basically, if our temperature is like 100 degrees, it's going to hit 100 degrees, the temperature is going to turn off, it's going to hit 99 degrees, it's going to turn on, and it's just going to keep bouncing between those two, just kind of for infinity, which is fine because we're trying to keep it at that temperature. I'm sure there's like some really advanced like control systems equations where you can like maximize how effective that input and output is. I'm sure that's something we're going to be working on next semester. Whoa, can't wait. So now taking a look at our stirring, we can see we have power. Our container is full. Normally this would be is not full, but again it is inverted on this side, so we are fine. It is not at temp yet, so we are going to go ahead and start this, and it will begin stirring. So moving down the line now that it's stirred, once it has hit this at temp thing that we talked about before, or once it's hit temperature, it will go ahead and trigger. Whoops, I actually forgot the at temp. See, it's a good thing we're taking a look at this. I forgot to put the at temp auto locking variable in here. So I will just scoot all of this down a bit. Ciao. And just add one little rung right here. That is just the temp at temp. At temp. And how does this turn off? This turns off once the timer turns it off. So TON1.Q, and that is normally closed. Okay, my bad. So at temp is not active right now, so it stirs. The moment our temperature hits for the first time, power is going to go through here. Our timer is not gone off, so we're going to go through here, and we're going to activate at temp. This is going to circumvent it and make it permanently on. So again, even if this temperature goes off, we are fine. This variable is going to stay... the variable is going to stay on no matter what until our timer turns it off. So now at temp has gone off, which means we lose signal to our stirring, but our heating is still on. Because we have also hit at temperature, power is on, at temp is on, and our timer is going to start. So this is going to wait around for 30 minutes. Just to show off, power is on and our timer is off, so the signal is going to stop there. Once 30 minutes have elapsed, that is going to change around how our circuit is working. So we can see now that our heater is going to turn off because the timer is now activated. We can also see that stirring is going to stay off. Is stirring going to stay off? Notice how we disable at temp. Because at temp is off, we can now actually see that stirring turns back on. So we need to add something to this to make it stay off. So what I'm going to do is I'm going to say at temp and also as long as V out is not on. So little addition there means that even now at temp is off, V out will actually turn on the moment that this activates because our tank is not empty because we've used that negative limit switch up there. V out is now activated. This is also activated. So because this is activated, our stirring will stay stopped. It's a good thing I double checked that because that would have been incorrect. And a lot of this comes down to like playing around with it and kind of learning. And like I said, it's very possible for previous things in your code to go wrong because it's hard to imagine every possible state that your system can be in at any given time. So it's good to like look through this or simulate it if you have that opportunity. But I don't, so I'm just running through by hand. So now V out is emptying our tank. Once our tank is emptied, this is going to untrigger. Now that that is untriggered, we can see our tank is not full. Because it's not full, none of these can run. You are off. You are off. Yep, because none of those can run, this can run. And we've reset our system. And it's just going to keep doing this over and over and over as many times as it need to until you hit this stop switch. Once you hit the stop switch, the power gets deactivated. Once power is deactivated, we lose everything here, and everything turns off. As a matter of fact, with that being said, I didn't have a power switch here. I would recommend putting a power switch there. And yeah, that is the solution to the problem that we're going to be going with for now that would control this system. Again, it might not be the most efficient. I still don't exactly know what's more important to prioritize when making ladder logic, if it is the amount of rungs or the amount of coils that you're using. But hopefully this gave you an insight on how to design something for ladder logic, how to take it from the physical system and convert it to the digital system, and how to kind of run through it in your head and see where you might have made some errors. So yeah, I hope you guys learned something. I didn't expect it to take this long, but hopefully, again, somebody gets something out of this. Other than that, have a great night, guys, and I will see you the next time somebody asks me to make a video on something.